Okay, so welcome to Math 5 Abstract Algebra. And so this is the most enjoyable part of the semester where we talk about the class mechanics, right? Yeah, I know this is what everybody's been waiting for. So we're going to move at a decent pace. Class participation 5%, homework 15%, midterms, if there's more than one midterm, unless you tell me otherwise, I will drop your lower midterm. There has been a time in my life where somebody did not want me to drop their lower midterm. I will explain privately when things are not being recorded as to how such a situation could actually arise. Final 40%. If you want to try to do a project for 10% of your grade, happy to do that. If you want to do a bigger project for even more, happy to do that as well. If you're doing really well with the material and you're understanding everything, rather than doing some standard exercises, if you want to try to push yourself in something, absolutely fine. I do a lot of undergraduate research. There's the small program, which is happening every summer here at Williams, but I also have an online version that I do with some colleagues where anybody who has taken a theory class is accepted. And you can do this in addition to other jobs over the summer. So if any of you want a research experience this summer, you are all accepted into the online program right now, just because I know you've taken a class that has theory. And it's something that you can do in addition of other things. I will provide more details on stuff like this. The prereqs for this class are Calc 3, basic combinatorics and set theory, and linear algebra. So we're not going to use too much of the material of calculus or linear algebra directly, but what we will be using is the idea of how do you attack certain problems, how do you do proofs. This is one of the two core classes for the major. I was a postdoc at Brown for 4 years. You did not have to do real analysis to be a math major at Brown. You did have to do abstract algebra. You did not have to do it. Now, I saw at least one eyes go, well, my eyes went like that when I arrived at Brown. But what I realized is, look, anybody who's going off to math grad school, they're of course going to do real analysis. This made the math major more accessible, and it guaranteed that anybody who went through it had at least one. You can still argue as to whether or not somebody should be a math major without having seen real analysis. But we want you to have at least real and abstract at Williams. These are two somewhat different subjects, different ways of looking at things, but both of them involve doing lots of proofs. And proofs are hard. The more times you do it, you start to recognize eventually, this is a technique. This is a way of attacking a problem. And that's why I really like the idea of trying to do lots of problems here, not just lectures, but more interactive. This would require you to make sure that you're understanding the material. Now, if we're doing a lecture on, well, I'll get to this in a moment, but anyways. So that's, the general administrative area. My office hours, if I'm in my office, it's office hours. My daughter is unfortunately sick, and I'm often in flex in the afternoons and not around. So I can always do things by phone and by Zoom, but if I'm around, it's office hours. Email me, happy to try to find a time to make things work. Some general advice first for me, then for my brother. So I had two thesis advisors. One of them was Peter Sarnak. And if you're an academic, it turns out what you really want for your birthday as you get older is a conference in your honor. And so mathematicians, physicists, we all have lots of conferences. And so for my advisor's 61st birthday, there was already a Steve Miller on the advisory committee because he actually had two thesis students named Steve Miller, born same year, same city. Now, the other Steve Miller is younger than I am and smarter. He skipped several grades, and he was actually graduating when I was arriving. It was wonderful for me because it made a reputation for me that, wow, your Sonic is so great. He's lapping everybody. He's on his second Steve Miller. And so people knew me, but we knew that it would not be good to have two Steve Millers on the organizing committee, but I still helped out. And so there's a big dinner at the Institute for Advanced Study, and we have had a couple of people alerted ahead of time. Would you like to say a few words about the guest of honor? And I said, of course. And I was not one of the people asked. I was not insulted. I'm surrounded by many of the top mathematicians of the world. There's only so many speaking slots. But I prepared a speech just in case. And I was very glad a few minutes after the big guns finished speaking, where they then went into the audience and handed the mic to a couple of people and said, would you like to say a few words? And they handed the mic to me. I would like to believe that I've been a professor long enough and he's meant so much to me that I could have said something very nice on the spot without any preparation. But it was a really good feeling that I had prepared something at that moment and I knew what I was going to say when I was given the mic. And so some of the best advice I can give you is be prepared. You do not know when an opportunity will present itself. This is a small class. You have a chance to get to know me well. This is one of the advantages of being at a school like Williams. Try to get to know at least one professor well every semester. That way, if you are only successful half the time, by the time you graduate, you will have 3 or 4 professors who know you well and can provide opportunities to you. Just last night, I got an email from a former student of mine. He's studying in England this year. He's decided he wants to pause going for a PhD for a couple of years and try industry. He's interested in the following. Do I have any suggestions of people to connect with? Of course. So you're shoot out an email. Within 2 minutes, several of my contacts, oh yeah, he looks great. Let me get him. This is the Williams Network. We are the oldest alumni society in the country. You want to take advantage of stuff like this. So you do not know when opportunities will happen. Related to this, I do not like getting emails less than 24 hours before an assignment is due saying something has come up. Now, if something truly spectacular has come up, I've just been invited to the White House. I have tickets to the World Series and I have an extra ticket for you and your family. If things like that happen, of course. But most of the time, these are things that can be predicted. I'm on a sports team and I've known for a while that we might have a game depending on how other games pan out. You try to get your work done in advance, or if it looks like you're not going to be able to do it, then you alert me well in advance and say, hey, Professor Miller, there's a chance I'm not going to be able to hand in the homework when it's due. Can I have an extension just in case? And I really want you to learn this so that when you go into the real world, you do not tell your boss less than 24 hours beforehand that you're not going to be ready. That's not going to go over well. So be prepared, budget your time, build up strategic reserve. Right now, not much is going on in a lot of classes. This is your chance to read ahead and build up. So your job is to be prepared for class. So if we are doing a section on Stirling's formula, what do you think you should know when you walk into the class? Stirling's formula. You should not be able to prove it, but you should at least know what is the statement of Stirling's formula, maybe why we care about it. Maybe have some idea of what the proof is and try to get a sense of maybe where was the difficulty. One of the things I really want to try to emphasize in the class is detecting where that miracle occurs. What is responsible for some of the good formulas we see? So always, come to me, come to the TAs, and come to each other with questions. So my job is to be available, to provide whatever resources you need, and to try to ask guiding questions so that you can get comfortable with coming up with things on your own. The goal is for you to eventually get to the point where you can generate good mathematics. So here's advice from my brother. So party less than the person next to you. Take advantage of office hours and mentoring. When you get out into the real world, it is not going to be as easy to have interactions with people as it is at Williams. Take advantage of that and learn to manage your time. No one wants to do that. It is amazing how many intelligent people cannot get things done on time and lose out on opportunities because of that. I assume there's no seniors here. Okay. Eventually, you might start applying for jobs and whatnot. If anybody wants to do practice interviews, I'm happy to do practice interviews. As I said, happy to adjust deadlines so long as you give me some heads up. So I talked a little bit about trying to find where the miracle occurs. So part of this is notation, part of this is images, is trying to look at things and quickly see what's going on. There's just so much going on sometimes, it can be overwhelming. If I give you a function f, how would you represent its derivative? So how would you represent the derivative of f? There's lots of answers. Anybody want to give me a notation for how they would represent the derivative of f? Good, so we could say f prime. That's great notation because it says it's somehow related to f. And when I look down at it, I can see there's a relation. This doesn't generalize well to several variables. Well, what if I taking the derivative with respect to x, with respect to y, with respect to all of them? What if I wanted to talk about the antiderivative of f? What would I write? Or what would I typically write? Or I could prime you a little bit and say, I give you a function lowercase f. How would you represent the antiderivative? Capital F. And if we use that as our convention, then when I'm looking at formulas, I can quickly see the relationship between the two. One of the worst lectures I ever went to as an undergraduate it took me a long time to realize that the f on the left-hand side was not the same as the f on the right-hand side. You should not use the same letter for two different things in the same equation. It was horrible notation. You want notation where you can quickly glance down and see what is happening. Similarly, when you have pictures of whatnot, you want to try to get a sense of where's the miracle, where's the action, where's the interesting things happening. So I would say there's a small number of interesting points on this. So this was from a lecture I gave in probability back in 2019 in the fall. Distribution of sunrise and sunset times in North Adams, the closest metropolis, to Williamstown. Does anybody notice anything interesting about this plot of sunrise and sunset times? Yeah, there's two jumps, and I would say maybe also it goes to decreasing, then all of a sudden starts to increase. Whereas here it's increasing, then all of a sudden it's decreasing. So I would say there's three potentially interesting points. Can anybody explain what the jumps are? Yes, it's daylight savings. All of a sudden the Earth's orbit doesn't have this incredible shift. What's going on is this is a clear way of seeing daylight savings. Right? So when I'm looking at this, I'm immediately focused on what's going on at those 2 points, maybe what's going on at this point as well. The other points seem to just be normal. So here is a picture of the lower 48 states as to who were they rooting for in the Super Bowl between the Patriots and the Los Angeles Rams, or if not who they were rooting for, who were they rooting against? So over here, you either have people rooting for the Rams or rooting against the Patriots. If you look at this, who's rooting for the Patriots? Which parts of the country? New England. Does that make sense? Yes, New England should be rooting for the New England Patriots. Okay. Anybody else rooting for the Patriots? Louisiana. And there's one other place that's rooting for the Patriots. You need to have somewhat good vision. Anybody know where that is? It's a city, it's St. Louis. There's a story behind those points. The Los Angeles Rams used to play in St. Louis. That explains why you have people over here. I wouldn't say they're rooting for the Patriots, I would say they're rooting against the Rams who moved. For the other one, for Louisiana, why is Louisiana rooting for New England? You need to know a little bit of football history for this. Does anybody know? In the conference championship game in the NFC, the New Orleans Saints played the Los Angeles Rams, and there was a horrible officiating error where they missed a pass interference that should have been called against the Rams and should have given the Saints the game. And so the people in Louisiana were furious. And in fact, I have a friend who's a writer for the papers down there, sent me some of the headlines, which were wonderful. And he said that when the Super Bowl happened, a lot of the bars did not broadcast the Super Bowl. They actually broadcast old Rams Super Bowls. They were so pissed with what happened. The NFL had to issue an official apology saying, yeah, we really blew that. Yeah. So when you're looking at things, you want to try to quickly look at where is the key. A lot of times it's going to be, I just have to do a lot of algebra. If I do enough algebra, things will work out. Where do I have to be clever? Where's the key idea coming from? And you want to quickly be able to glance down at things and see what's happening. All right, so what I want to do now is I want to try to motivate abstract algebra. I think we have till 11:10 by talking about one of my favorite applications, cryptography. So out of curiosity, who here has seen some cryptography? Okay, who has seen a lot of cryptography? Did you take a class or? Okay, yeah. Okay, so you've seen a lot. Okay, excellent. So briefly, there's a lot of goals in cryptography. Part of it is we want to transmit information so that only the intended recipient can decipher it. Related to that, we might want to transmit that information quickly. We might want to be able to do all the actions in a reasonable amount of time. There's a lot of things in mathematics which are trivial, but we can't do in a reasonable amount of time. So does everybody know what a prime number is? So the correct definition is a number is prime if it has precisely two distinct factors, one in itself. We don't want one to be considered a prime. So if I want to figure out if a number is prime, can somebody give me an algorithm to tell if a number is prime? It's okay if the algorithm is bad and slow. Great, great. No. As soon as you say square root, you're being somewhat clever, right? Just check every number less than it and see if any of them divides. And so that will tell you if a number is prime. It will take a tremendous amount of time for a good-sized number. You can then start to do things that are a little bit clever and say, well, if my number is composite, I can write it as a product of two numbers. At least one of them has to be less than the square root of the number, or the product is too small. And if I know that the number is not divisible by 2, it's not divisible by 4, there's no reason to check any even number. If it's not divisible by 3, it's not going to be divisible by 9. I can do stuff like this. It's not going to help tremendously. It'll help a little bit. It's trivial to tell if a number is prime, pure mathematics. It is hard to tell if a number is prime by this method in applied mathematics in a reasonable amount of time. If you're doing an online transaction, you don't want to wait 15 years for them to verify your identity and ship the product to you. You need to be able to do this quickly. The other thing is, you want to authorize your bank, your credit card to transfer money on your behalf to the company, and then they'll send you the product. You don't want someone else to pretend to be you and purchase things with your credit card. So you need ways for people to verify that you are who you say you are. And so this is another big part of cryptography. How do we transmit information in such a way that the recipient can be assured that it is coming from us? And so what I want to do now is talk a little bit about an introduction to cryptography as a way to motivate the material in abstract algebra. So again, I was trained primarily as a number theorist, so my go-to is number theory. If there are other areas you want to see, I'm happy to work those into the lecture as well. Any mechanics? Okay. So what I want to do is I want to talk about some of the oldest methods of encryption. So this is going back to ancient Roman times. Back then, it was almost enough just to write down the message so few people could read. But let's try to do a little bit better than just writing things down. So we're going to talk about the Caesar cipher. So I'm going to look at a function from the alphabet to the alphabet. And so you give me a letter, and I'm going to encrypt it. I'm going to send a letter to another letter. Eventually, we're not going to send letters to letters. We're going to send numbers to numbers. We're going to represent letters of the alphabet with numbers because as mathematicians, we would much rather work with numbers. You can add two numbers. What's 2 plus 5? This is like the marshmallow question. 2 plus 5, guys, come on. 7, right? 2 apples plus 5 apples. Maybe 7 fruit. You can't add apples and oranges, but if you convert everything to numbers, we can do that. We can do a lot of manipulations with stuff like that. So here's my question. I want to look at all ways to encrypt a message. So I'm going to send each letter to each letter. How many choices do I have for A to go to? So how many choices are there for A? I'm sorry? Well, no, I'm just saying, well, right now, how many places can I send A to? How many options for A? It's not 25. It's close to 25. Why can't A be sent to A? Oh, different letters go to different letters means like A and B don't both go to C. Then you can send it A. So there's 26 choices of what we send A to. How many choices, once we've determined what A goes to, how many choices are there for B? So it's 25. And then how many choices for C? 24. So this is 26 factorial. So as an exercise, try to see just how big is 26 factorial. It's a decently sized number. That's a lot of possibilities. We're going to look at some very simple ones. Now, here are 2 conditions on my wish list. I want different letters to go to different letters. So I want A and C to go to different letters. I don't want A and C both to be sent to Q. That seems reasonable, because if they're both sent to Q, if I receive Q, I won't know what it came from. And I want every letter of the alphabet to be hit. Do I need both of these conditions, or does one condition imply the other? If I know different letters go to different letters, does every letter get hit? If every letter is hit, do different letters go to different letters? What do you think? Do you think I need both of these conditions, or does one condition imply the other? Are they equivalent? What are your thoughts? Somebody give me a letter. Q. All right. So imagine we don't have the letter Q. Only 25 letters are hit. We don't hit the letter Q. But there are 26 letters in the alphabet. Is it possible for different letters to go to different letters if Q is never hit? No. So this is the famous Dirichlet pigeonhole principle, or the box principle. Imagine you have n+1 pigeons, and you carefully place them in n boxes. There's no way to do this without having one box get at least 2 pigeons. So if I have 10 pigeons and only 9 boxes, at least one box has to get 2 pigeons. Because if each box only gets 1 pigeon, there's 9 boxes that can only account for 9 pigeons. 1 is left over. So if I don't hit all the letters, if I don't hit Q, I've got 26 letters, and they can only go to 25. So at least 2 letters have to go to the same letter. It might be the case that 3 letters go to the same, but I know at least 2 go to the same. So if all letters are not hit, then different letters will not go to different letters. Conversely, if different letters do not go to different letters, then we're not going to get all the letters to be hit. So it's a nice exercise, try to write out formally that these 2 statements are equivalent. One of the big things we have in mathematics is sometimes trying to see what is the minimal set of conditions we need for something. So when we get to a group, we can say, what do we want the definition of a group to be? And sometimes we say, this is a good definition, but maybe at a higher level, you might say, well, actually, we don't need all of these conditions. We can actually have something that's a little bit more minimal. Now, the big danger in mathematics is whenever you see an infinity. Whenever you see an infinity, things are very different. If I had a 50-letter alphabet, this would still be true. If I had a 1,000-letter alphabet, this would be true. But if I had an infinite alphabet, let's say my alphabet is 0, 1, 2, 3, 4, 5, the non-negative integers. I could come up with a way to send different letters to different letters, but every letter is not hit. Send 0 to 1, 1 to 2, 2 to 3. Or send 0 to 0, 1 to 2, 2 to 4, 3 to 6. There's lots of ways to do this. So as soon as I have an infinity, these 2 conditions are actually different. So for a finite alphabet, I could get away with saying these are the same, but for an infinite alphabet, no. So you always want to be careful whenever you see an infinity. So a little bit of notation, if x is the input letter, let's let f of x represent the encrypted letter. So I'm going to have some function, you give me an input, I'm going to give you an output. What's the simplest function you can think of? And again, in my class, it's okay to be a smartass. What's the simplest function you can think of for f of x? X, right? You give me an input and I give you back that as your output. That will clearly work. Different letters will go to different letters. Everything will be hit. It's not going to be hard to decrypt this, right? Because your message is just the message. Now, another simple function we could do is we could send every letter x to a fixed constant c. Why would this be bad? So what would be bad about sending every letter to the same letter? Yeah, every message would be sent to C, 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 C. I couldn't tell anything. But we could combine these 2. Let's take f of x to be x plus c. So this is the simplest function I can think of that has a chance of being interesting. So what this is doing is it's shifting every letter. And this is where it's nice to think about things as numbers. But let's say c equals 3. Then I'm going to shift every letter down by 3. So A shifted down by 3 is D. B shifted down by 3 is E. W shifted down by 3 is Z. Now it gets interesting. What if I try to shift X by 3? X goes shift by 1, I get Y. By 2, I get Z. What letter should come after Z? Hey, we're going to go basically around the clock. So let's round down. Let's say it is 10 o'clock right now. What time will it be in 4 hours? 2. So you're in a 300 level math class and you've just told your professor that 10 plus 4 equals 2. Yes? Okay, and you're confident with that answer? Yes. So does 10 plus 4 equal 2? Module, on a clock with 12 hours, yes. On a clock with 12 hours, 14 and 2 are indistinguishable. So this leads to the notion of equivalence. For a lot of things, I only care about certain properties. I don't care about all the properties. I just care, are they the same for these things that I care about? And if the answer is yes, then we'll say that they're equivalent. And so on a clock, 14 and 2 are equivalent because they differ by a multiple of 12. For the alphabet, how many hours would be on the alphabet clock? It would be 26. And so on the alphabet clock, after Z would come A. And so if I shifted X by 3, I would get A. So how would I decrypt a message here? So if I encrypt the message by shifting forward by 3, how would you decrypt? Yeah, just shift back by 3. Is it hard to shift back by 3? No. So this is going to be very straightforward. I can write it out linearly like this. A goes to D, B goes to E, and so on, and just keep cycling and wrapping around. Or if you want to do a little bit better tech coding, I can actually do it as a wheel. I actually much prefer this, and you can really see how I'm just going round and round and round. A goes to D, B goes to E, Z goes to C, and then after Z, I'm coming back to A. And so if I wanted to actually do this, if I give you a message, let's say meet at 10, I can just convert all the letters to numbers. I can then add 3, and then I would transmit that message. And if you wanted to decrypt, you would just subtract 3. Well, this is if you know how it was encrypted. What if you don't know that it was encrypted by shifting by 3? You just know that it was encrypted by some kind of shift. Would it be hard for you to decrypt it? So what could you do if you don't know how it was, if you don't know what the shift was, you just know that it was somehow shifted? How would you try to crack the code? What could you try to do? Yeah, keep shifting. Shift, and how many shifts would you have to try? Worst case scenario. Well, no. Let's do it really straightforward for you. I received this message. What should I first try shifting by? I should try shifting by 1, and then if that doesn't work, try shifting by 2. And so there's really only 26 things to try, or maybe 25, because I'm going to assume you did some shift and you're not just sending me the message, right? So there's only 25 choices. That's not that bad. So here is a proposed solution to make the Caesar cipher more secure. So there are 26 possible shifts, 25 if we don't do the trivial shift. So let's say 25 shifts. What I'm going to do is I'm going to choose 25 different shifts at random and keep that secret. And I'm first going to shift by C1, then by C2, then by C3. I'm going to do this 100 times. So how many ways are there to choose 100 different shifts? So there's 25 choices for the first shift. How many for the second? 25. How many for the third? 25. So there's 25 to the 100 possibilities. There's only around 10 to the 80, 10 to the 90 particles in the universe. This is far vaster than that. So when I just gave you this message, there were only 25 things for you to try. You can do that by hand. That's not so bad. Now we're talking about 25 to the 100 possibilities. Is that secure? Can you go through all 25 to the 100 possibilities? in a reasonable amount of time? So is this a way to make the Caesar cipher secure? Just choose 100 different shifts. Does this work? What do you think? Have we now made the Caesar cipher secure? Let's say the message is at most 50 characters. We've got 25 to the 100 possibilities. If I shift by 2 and then I shift by 5, what's that the same as? 7. If I shift by 2, then by 5, then by 1, it's the same as shifting by. So if I do 100 shifts, it's the same as just shifting by their sum, and then you just remove as many multiples of 26 as you need until you get something between 0 and 25. So if I do 100 shifts by the Caesar cipher, it's really equivalent to just doing 1 shift. How long will it take you to crack this? There's only 25 things to try. It's actually no more secure than doing 1 Caesar cipher. It seemed like it was more secure at first, because I have 25 to the 100 possibilities, but so many of these possibilities are the same. There's only 26 buckets they can go into. This is one of the things you have to be extremely careful when you're doing cryptography, is that you might have something that seems secure, but there might be an easier way of doing the calculation than you thought of. And that turns out to be the case here. The Caesar cipher with 100 consecutive shifts, it's equivalent to just 1 simple one. So the shift of a shift of a shift of a shift is just another shift. And this is one of the things we'll be looking at in group theory. When we have objects and structure and we keep iterating, we'll still have something without structure. Okay, so let's try to make things a little bit more complicated. We looked at f of x equals x plus some constant. Now let's look at a times x plus a constant. And let's see how many choices we have. So we want to know what a's are possible, what b's are possible. I always like to look at simpler cases first and then expand from that. So rather than looking at a 26-letter alphabet, let's assume we have a 6-letter alphabet. So how many hours will be on our clock if we have a 6-letter alphabet? It'll be just 6. Now, whenever you have something that's complicated, try to break it down into lots of simpler things. So what do I have here? I have a times x plus b. I already know what the plus b does. That's just the Caesar cipher that's just shifting everything by a fixed amount. I can easily understand the plus b. It's the a times x that's more complicated. So if I can figure out what's going on with the a times x, I can then put in later the plus b. So for the b's, we can shift by 6 possibles, 0, 1, 2, 3, 4, 5. Or if you want 1, 2, 3, 4, 5, 6. You can either start counting with 0 and end at 5, or you can start counting at 1 and end at 6. Either one is fine. Now, let's look at the possible a's. So, which a's work? And so, let's do some calculations. So I claim we might as well just assume b equals 0 because I can always plug that in later. Let's look at a times x. So I need different letters to go to different letters, or I need every letter to be hit. And so if we take a equals 1, then that clearly works, because the numbers 1, 2, 3, 4, 5, 6 just go to 1, 2, 3, 4, 5, 6. Now let's take a equals 2. 1 goes to 2, 2 goes to 4, 3 goes to 6, and I claim 4 goes to 2. 4 times 2 is 8. What is 8 on a clock with 6 hours? It's just 2. And then 5 times 2 is 10, which is just 4 on a clock with 6 hours. And then 6 times 2 is 12, which is the same as 6 on a clock with 6 hours. So this is enough to tell us that 2 fails. I don't have different letters going to different letters. Both 1 and 4 go to 2. 2 and 5 go to 4. 3 and 6 go to 6. I also don't have all the letters hit. Now, what's nice is as soon as I know that 2 fails, I also know 4 and 6 fail for A. And the reason is 4 is just 2 times 2. 6 is just 3 times 2. So once I know that if I multiply by 2, I no longer have distinct letters, then it's clearly still going to be having issues if I now take all of this and multiply by 3. In fact, it's going to be even worse. Everything is going to be sent to 6 now. But I know once it's bad with 2, if I then multiply by 2 or by 3, it's still going to be bad. So I don't have to check 4 and 6 separately, but if you check them, it's not a big deal. What about 3? 1 goes to 3, 2 goes to 6, 3 goes to 9, which is the same as 3. 4 goes to 12, which is the same as 6. 5 goes to 15, which on a clock with 6 hours is just 3. And then 6 goes to 18, which is just 6. So we see that 3 fails. If I try 5, 5 works. 1 goes to 5, 2 goes to 10, which is 4. 3 goes to 15, which is 3, and so on and so on and so on. So 1 and 5 work. 2, 3, 4, and 6 fail. Can anybody tell me what property 1 and 5 might have that's causing them to succeed, whereas 2, 3, 4, and 6 fail? I'm sorry? So we say two numbers are relatively prime if the only factor they have in common is 1. And the reason we don't want to obsess about, well, 1 divides is if we consider that, well, every number is divisible by 1. And so you would never have numbers that are relatively prime because they would always share 1 as a factor. It's just like big deal. Okay, you're both divisible by 1. I'm really proud, right? Every positive integer is divisible by 1. So I don't want that to be part of my condition. So we'll say two numbers are relatively prime if the only factor they share is 1. And what we notice here is that 1 and 5 are relatively prime to 6. 2, 3, 4, and 6 all share a non-trivial factor with 6. Maybe that's what's going on. Maybe that's why 1 and 5 work. So let me just check people's algebra skills. So can somebody tell me 16 over 64 in lowest terms? 1/4, excellent. 19 over 95 in lowest terms. 1/5, excellent. Let's do 2 more. 49 over 98. Do the harder one. 1/2. All right, let's do one more. 12 over 24. Sorry? I can't hit it. I get 1/4. Does anybody else get 1/4, or is it just me? Just me? Should I show my work? All right, 16 over 64, cancel the 6s, it's 1/4. 19 over 95, cancel the 9s, it's 1/5. 49 over 98, it's 4/8, which reduces to 1/2. So clearly, the way you divide numbers is you cancel across the diagonal when they're equal. So 12 over 24 equals 1/4. Yes. That is also one of my favorite ones. It's usually done as the limit as n goes to infinity. And you cancel the ends and it's just equal to 6. Just because something works for a while does not mean it's going to continue to work. That doesn't mean it's worthless to gather data. I'm a strong proponent of gathering data, but you've got to be careful. And you might not be looking at generic cases. What I could do is I could keep, say, 19 over 95 or 49 over 98 in strategic reserve. And maybe what I do is I just give you the first two. And you say, hey, Professor Miller, 12 over 24 is not 1/4. All right, well, let's choose something else. I don't know. Let's try, 49 over 98. Yeah, it is 1/2. So you can keep something in reserve. So just because something works for a couple of cases does not mean it's going to keep working. So you want to gather more and more data. And so we can go back, and it looks like what's going on is just the numbers that are relatively prime. It turns out that that's true, and we'll prove that later in the semester. The only A's that work are those relatively prime to the number of hours on the clock. Okay, so if we now do a 26-letter alphabet, how many numbers do you think are relatively prime to 26? Or can you give me some numbers that are going to share a factor with 26? 13, good. What else? All the evens. So we lose all the evens, and the only odd we lose is 13. So the number of choices for A would be 12. And so it's going to be all the odds but 13. So there are 12 choices for A. And then we're doing f of x is ax plus b. There are 26 choices for b. So there's 312 choices. One of these choices is a is 1, b is 0. That's trivial. So there's 311 non-trivial choices. It's not as easy to do as the 26 choices with the C as a cipher, but 311 choices is not a big deal. You know, humans can do something like that. Humans can crack codes like this. So the question is, what can we do to make things more secure? Can we use higher polynomials? What else can we do to make things more complicated and harder to break, to give us more possibilities? So I want to introduce some notation. So we're going to meet this function a lot throughout the semester. It's the Euler-Totient function. So the function phi of n represents how many numbers from 1 to n are relatively prime to n. So that means the only common factor they can have is 1. So what we want to do is we want to try to get a sense of what is phi. And when you do problems like this, it's often good to try to do it with some simple numbers first, and then try to get some intuition, and then build up. So the simplest number I can think of is a prime. So imagine I give you p equals 5. So 1, 2, 3, 4, 5. Which of these numbers are relatively prime to 5? Or which of the numbers are not relatively prime? Let's do not relatively prime. What's the only one we have? What's the ones we have to get rid of? Yes, we have to get rid of 5. So here we would see phi of 5 is 4. If I give you p equals 7, I'd have 1, 2, 3, 4, 5, 6, 7. What are the only numbers that share a factor with 7? It would just be 7. And so we would get, phi of 7 is 6. This is 2 data points, but hopefully the pattern is clear. If I give you a prime number, how many numbers between 1 and p are relatively prime to p? What do you think? P minus 1, perfect. It would just be p minus 1. So now we have 2 choices of where we can go next. I could look at p squared, or I could look at p times q, where p and q are 2 distinct primes. Let's do p squared and see, let's say, for instance, p equals 3. Let's do 1, 2, 3, 4, 5, 6, 7, 8, 9. Which numbers do I lose as having a common factor with 9? So what would I lose? Yep, 3, 6, and 9. So so the answer here would be 9 minus 3, or 3 squared minus 3. If I give you p equals 5, I would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 25. Which numbers would I lose now? So what would I lose now? 5, 10, 20. So how many numbers do I lose? I lose 5, or 5 squared minus 5. I lose 1p, 2p, 3p, all the way up to p times p. And so what would you guess the formula would be for phi of p squared? P squared minus p. And then as an exercise, I'll leave to you, try to figure out what do you think the formula might be for phi of p cubed, phi of p to the 4th, phi of p to the 5th. And so we can come up with formulas for phi at a prime power without too much trouble. What if I give you 2 distinct primes? Now things are a little bit more interesting. And so again, think back to the example of 16 over 64. We want to be very careful about what we deduce from few experiments, but it's still worth doing the experiment. So if we take p equals 2 and q equals 3, we get 1, 2, 3, 4, 5, 6. And down here, I'll do P equals 3, Q equals 4. Oh no, I'll do 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, I don't know if I said this. I will be posting all of the slides and all of the videos sometime after class. So which numbers do I lose for 6 that are sharing a factor with 6? So which numbers share a factor with 6? A non-trivial factor, yes. 2, 3, 4, and 6. And so now it's a little bit more interesting. How do I represent this? Well, phi of 2 is 1, phi of 3 is 2, phi of 5 is equal to 4. And I'm just using phi of a prime is 1 less than that prime. So now, over here, I've got phi of 6 is equal to 2. How might you represent that in terms of phi of 2, phi of 3, phi of 5? Which ones do you think matter? Yes, what do you think the answer is? That's definitely a reasonable conjecture. If I look at what's going on now for P equals 3, Q equals 5, which numbers do I lose? So which numbers would I lose as sharing a non-trivial factor with 15? 3. So I think it's easier to first remove all the 3s. I lose 3, I lose 6, I lose 9, I lose 12, I lose 15. Now let's do the 5s. And so now what would I lose? 5, 10, and I actually lose 15 again. Even though I've lost it again. And what can you say about phi of 15? So phi of 15 is going to be 8, and that is phi of 3 times phi of 5. So if you look at this, you might think maybe phi of a product is the product of the phis. It's definitely held in these two cases, but maybe we're looking at very special cases. If we take P equals 2, phi of 2 is just equal to 1. And if I give you 1, 2, 3, 4, which numbers share a factor with 4? So which numbers do I have to throw away? 2 and 4. Uh-oh. We get phi of 4 is 2, which is not phi of 2, phi of 2. So it's always good to try to do some small cases and build intuition. This is enough to show us that it's not always the case that phi of a product is the product of the phis. It turns out that this is true if the product is two relatively prime numbers. The difficulty here is P equals Q, they're both equal to 2. And we were able to find this by looking at a very small example. So going back to our analysis, if P and Q are distinct primes, we think that maybe phi of PQ is phi of P times phi of Q. We've only done that for a couple of cases. We could do a few more, and every time we do it, it's looking like phi of PQ if they're distinct primes is the product. Let's quickly prove this. So what we can do is we can list all the multiples that we're going to lose. Well, if I share a common factor with P times Q, I'm either a multiple of P, I'm a multiple of Q, or I'm a multiple of both. Which are the multiples of P? P, 2P, 3P, 4P, and so on. So how many multiples of P do we have? We have Q multiples of P. So I'm losing, that's why I have PQ minus Q on the bottom. I've lost Q multiples of P. What about multiples of Q? I lose Q, 2Q, 3Q, with my Boston accent, I'm not going to say the next one, all the way up to P times Q. I lose P multiples of Q. And that's why I have the minus P in the bottom. Why do I have the plus 1? I double counted PQ. I removed PQ because it was a multiple of P. I removed PQ because it was a multiple of Q. So I have to add it back. And that's why the number of numbers that are relatively prime to PQ is PQ minus Q minus P plus 1. One of the hardest things in mathematics is thinking, how do I simplify algebra? How do I write this in a more meaningful way? Well, I have an intuition that this is P minus 1 times Q minus 1. Let me just multiply P minus 1 by Q minus 1 and see if it happens to equal that. And it does using FOIL. But the intuition we gained by looking at lower cases, by looking at some small cases, was extremely valuable in terms of trying to figure out what is the answer here. Okay, so I'm going to skip the Vigneri cipher. I'm going to quickly try to motivate why do we use primes for encryption. So I'm going to give you two different schemes for encryption. So in the first scheme, I'm going to choose two 200-digit prime numbers, and I'm going to multiply them, and I'm going to make that product publicly available as n. And the password is going to be either P or Q. You give me either one of those, and I let you in. The second system is I'm going to choose a 5,000 random digit number that I'm going to keep secret, and the password is that 5,000 random digit number. Which do you think is harder to crack? The 5,000 random digit number, the second method, or give me one of the 200-digit prime numbers that divide n, and I'm going to tell you what n is. So which do you think is going to be harder? Would you rather guess 5,000 digits correctly or try to guess 200 digits correctly? Which seems harder? So you think it's harder to get 200 digits right than 5,000 digits right? So why would the 200 digits be harder to guess?
Well, I think 5,000 digits. Well, it's 11.
But there's still 10 to the 5,000 things to check. How many 200-digit numbers are there? There's 10 to the 200, basically 200-digit numbers. There's 10 to the 5,000, 5,000-digit numbers. Right? There's a lot more things. I could forget about the fact that they're prime. I can forget about the fact that they divide n. That's extra information, which might actually help me. There seems to be a lot more things to check if it's a 5,000-digit number. So which do people think is going to be harder to get? The 5,000 digits or the 200 digits? Does it seem like it's going to be harder to get 5,000 digits right? So let's think about how the computer will tell if you're correct. So the computer, in the first case, it knows the product. The computer does not need to know the factors. All the computer needs to know how to do is divide. And imagine you come to the computer and say, I know the password. Here's the password. What does the computer do? How does the computer tell if you have the correct password? So you're claiming to the computer, I know one of the two prime factors of your number n. Here is my claim. This is one of the two factors. What does the computer now do to see if you're right? Divide. It's very easy for the computer to divide. The computer does not need to know the password to tell if you're correct. What about the second situation where it's a 5,000 random digit number? How does the computer tell if you're correct? What is the computer going to have to do? What's the only way the computer can tell if you're correct? What does the computer need to know? The password. That's the difference between the two. Is the first one is I'll know it when I hear it. You can have a guardian that does not know the password but will recognize it. In the second one, the computer knows it. You could potentially torture the computer if you got hold of it and try to look, because it has to be written somewhere on it for it to recognize the password. So even though there are far more choices in the second system, because the computer needs to know the password to tell if you're correct, it's actually far less secure. And that's why we like to use primes. So I like to put things in perspective. So imagine every atom in the universe is a universe, and every atom in those is a supercomputer. And the supercomputer, let's say it's better than what we have currently available. Let's say it can check 10 to the 15 numbers a second. There's about 3 times 10 to the 7 seconds in a year. We could check about 10 to the 182 numbers a year. The universe is about 15 billion years old. So if every atom in the universe was a universe and every atom in those universes was a supercomputer running since the dawn of time, that gets us up to 10 to the 192. We're basically a factor of 10 to the 7 away from even getting up to 10 to the 200. And we do not have anything close to this level of computational power available to us. We do not have a universe of universes of supercomputers running since the dawn of time. So if you look at something like this, it seems like this would be extremely secure. If we don't have a good way to check if a number, to determine the factors of a number, there's just too many things to try. And so it turns out, very similar to the Caesar cipher, that sometimes there are better ways of doing things than we had seen. And we'll see examples of that later this semester, that things that people thought were secure turn out not to be. And there's a lot of very interesting mathematics that goes into this that we have to be very careful about. A lot of people have already shifted away from doing encryption based on primes because quantum computers, it turns out they can factor numbers quickly. Now, right now, good quantum computers have not been built. I can't remember if they're currently, the world record for the factorization of a quantum computer is either 21 or 35. These are not big deals to factor numbers like this, but it scales up nicely. And in a couple of years' time, they do expect the quantum computers to be able to break encryption based on primes. And so people have already started to shift away from stuff like this because even if it's secure today, people can intercept your messages and store them for later and find out what's going on. A lot of times secrets are classified for 50 years. Hopefully that's long enough that anything that comes out doesn't really matter. So I want to end the last 15 minutes by talking about RSA, named for the 3 creators of the algorithm. For years, this was the gold standard of encryption. It allowed us to transmit securely messages between people. We could even do it in such a way that I could verify my identity. It was absolutely wonderful. You always have to be careful when you talk about the history of cryptography as to who was the first one to discover it, because a lot of times people were working for intelligence agencies which did not publish who did what and when. So this is what was first publicly known. So it is common convention to name the people Alice, Bob. The only freedom you have is for the eavesdropper. Could either be Charlie or Eve. Why might you name people Alice, Bob, Charlie? ABC, you want things to be very easy. Typically, it's Alice is trying to communicate to Bob. I could put subscripts B in all of these to say that these are things that Bob is doing. Bob is choosing 2 secret primes. Say P is 15,217, Q is 17,569, and Bob chooses a big number D. And he keeps all of these secret. And then Bob makes public the product of the 2 primes, P and Q. We don't know a good way to factor. Okay? This is actually not a bad number to factor because P and Q are not too large. Imagine these are 200-digit numbers. I don't want to write 200-digit numbers. You don't want to read 200-digit numbers. So let's imagine these are big numbers, but for practical purposes to just do a calculation right now, we'll use small numbers. And Bob makes public a special number E. Any idea why I chose this number? Well, it's not quite pi, but it does look a lot like pi. What is pi? 3.1415926, and so if I round, that's 3. So when you look at this, maybe this E is chosen because it's related to pi. No. I chose this because E times D has a very interesting property. If I multiply E and D together, and I look at its remainder on a clock with P minus 1 times Q minus 1 hours, I get 1. Okay? And again, can you multiply these 2 numbers? Yes. If you know P and Q, you can subtract 1 and get P minus 1 times Q minus 1. And then you can divide the product of E and D by that and see that the remainder is 1. Nobody wants to do this, but you could do this, and your computer can do this very easily for you. So we'll talk later in the semester about how would you find the primes? How would you find two numbers E and D that have this relation? Is it always possible to find such numbers? Is it easy to? And this is how RSA encryption works. So Alice can send any message less than the number PQ, less than N. So let's say Alice wants to send the message 195632041. And again, what we could do is maybe we're sending 00 is A, 01 is B, all the way up to the 25 is Z. Maybe we then do those are uppercase letters and the ones after that are lowercase letters. Then we have the numbers, then we have some punctuation marks. So maybe every 2 digits gives me some symbol on the keyboard. So this could be the 20th letter of the alphabet, uppercase. This could be, it's 26, 31st, give or take, letter of the alphabet, lowercase, and so on and so on and so on. And if your message is longer than N, you just break it up into chunks of size N and you keep transmitting each one. And what Alice does is she takes her message and she raises it to the eth power and looks at what is that line on a clock with N hours? What's its remainder when we divide by N? Now, in practice, E is going to be of size 10 to the 200. It is very easy for me as a mathematician, as a pure mathematician, to say, oh, just raise M to the eth power and take the remainder. M times M is M squared, take the remainder. Multiply by M, that's M cubed, take the remainder. Multiply by M, that's M to the 4th, take the remainder. Trivial. The universe will die a heat death before we make any progress on it. But I'm a pure mathematician, that's not a big deal, right? If we're making a transaction on Amazon, different type of prime that we've been looking at today, we can't wait 3 years for them to confirm that they can send us the stuff. We need a fast way to calculate M to D, and it turns out there is a way to do this. Group theory and abstract algebra will come to the rescue. It will provide a good, efficient way to do this. And now Alice sends the remainder when we divide by N, which is 121209473. Bob takes that number and he raises it to his special D, which he's kept secret. And he looks at the remainder of that on the clock with N hours. And when the dust settles, Bob gets 195632041, which was the original message from Alice. So amazingly, we now have a way for Bob and Alice to exchange a message. The question is, can Charlie or Eve deduce what the message was? Well, what do they know? They know the product P times Q, and they know E. If they can figure out D, they can decrypt the message, because then they would know what to raise it to. So the question is, if we know E and we know P times Q, can we solve this equation for D? And right now, nobody knows a good way to do that. We don't know what P minus 1 times Q minus 1 is. We only know what P times Q is. So we don't even know how many hours on the clock should there be when we're trying to solve this equation. Now, there might be a really good way that everybody has missed. That's possible. I gave you the 100 Caesar ciphers in the beginning today. This is one of the things I want you to take out of this entire semester, and we did on the first day. Just because something looks hard doesn't mean it's hard. It looked like there were 25 to the 100 possibilities. Wow, this is a really secure way to do things. No, it's trivial to crack. You do this and I can read all of your messages without any trouble. So just because we can't find a good way to do it doesn't mean that there's not a good way. In this class, and this is why I want to do a lot of problems in the class, I want to try to break it up so maybe half the time you're watching lectures and reading the book, and half the time we're just doing lots of problems on the book. The more problems we do, the more the material will not only gel, but the more comfort I think you're going to get in actually proving things. That's how you learn. You try to prove things, and you start to get a sense of which approaches are going to work. Now, what's really interesting is imagine that there was a transmission error, and the last digit that Bob receives is correct, the second to last digit is wrong, and every other digit is right. There's one digit that's off. If I was transmitting a message with the Caesar cipher and one letter was off, not a big deal. If I have a text and I have one letter wrong, I can correct that. But over here now, if I have one digit that's wrong, remember, I'm now raising this to the dth power. think of that as raising it to the 10 to the 200. Being off by a little bit is enough so that at the end of the day, it's garbage. The message has almost no bearing, no relation when I decrypt it to what the intended message was from that one little small mistake. So it's now extremely important that we get everything right. So there's a lot of implementation issues. And throughout the semester, we're going to learn how to use abstract algebra to solve stuff like this. So again, one of the nice things at Williams is you get to choose for classes like this, what do you want your emphasis to be? You can do a lot of group theory in physics. There are people who are a lot of physicists, that would be one way to do the course. I don't think there's many physicists who are signed up for this course, so I didn't want to do group theory in physics. I wanted to do group theory and cryptography. This gets us not only number theory, but it also gets us modern e-commerce. So some of the implementation issues is how can we actually find large primes and how large is large enough? So a lot of it depends on the type of security you need. In World War II, if you were in a battlefield situation, you might need codes that would be secure for maybe 5 minutes to an hour. And you might be saying, we're going to attack the hill from the left side. And if an hour later, the other side determines what you said, well, that's fine. You've already done the attack. They know what you did. When you're planning invasions like the liberation of France, D-Day, this is a plan that's going on over months to years. You need something that's going to be secure for much longer. So depending on the situation, the level of security could be very, very different. How do we find an E and a D such that E times D equals 1 on a clock with P minus 1, Q minus 1 hours? It's not at all clear that this can be done. How do we compute M to the E efficiently? So all of these we will talk about how to do. The last one, can Eve determine D from E and N? If anybody knows how to do this, they've been smart enough not to say so. If you figure out how to do this, talk to me when it's not being recorded. Okay? Right now, no one has come forward with a way to deduce what D is from this information. That's one of the biggest challenges right now. But imagine we could factor quickly. Well, if we could factor quickly, then we would know what P and Q are, we would know what P minus 1 and Q minus 1 are, and then it turns out this equation is very easy to solve. And we can solve it rapidly, even if the numbers are of size 10 to the 200. There's very fast ways to solve it. But that's assuming we know this extra information. Some of the math related to this leads to one of the most interesting proofs I've ever seen. If I give you a number that's composite, how do you normally tell a number's composite? So how would you tell a number is composite? What would you give? What would you do? Look for its factors. So it turns out that a lot of the math we're going to learn in group theory, we can use this to determine that certain numbers are composite without giving a factor. That composite numbers have different properties than primes. Now, not every composite number, there's a very small set of composite numbers that cause trouble, but almost all composite numbers will have a certain property that we can detect. We won't be able to tell what their factors are, but we will be able to tell that they are composite. So this hopefully gives you, a little bit of a sense of what we're going to be doing in the class. We're going to be learning group theory, we're going to be learning rings, we're going to be learning functions, functions on functions. We saw Caesar cipher on a Caesar cipher is just another Caesar cipher. We're going to be trying to build up mathematical structures like this that generalize properties of the integers and the real numbers that you know, and we're going to try to apply them in interesting situations. So, again, a lot of this could be related to cryptography because this is both, number theory as well as e-commerce applications. But if there are things that you're interested about, please just let me know, and I'm happy to try to find a way to work that into the course. That's one of the nice things about teaching at a small liberal arts college. If I had 300 students, which I had when I taught at Ohio State, not as easy to make sure everybody gets hit. But if there's something that you're really interested in and you want to see more about, or if you want to do that as a project, just let me know. All right. So this is a good place to stop. So I'll stop the recording.